for the atmospheric column density of NO2 over Accra in Ghana from the OMI instrument, which is another instrument, which was operating since the early 2000s. So you can see this more than or now getting close to sort of a 20-year data record. And with that data record, you can really look at the trends and how these properties have been changing over time. And also just in terms of sort of public communication, it's often easier for people to look at an image like the one on the upper left here of the satellite data and very clearly gain at least a basic understanding of what's going on versus looking at, for example, the plot on the right, which you typically see with ground-based measurements over time, which maybe takes a little bit more effort for them to interpret and understand what's going on. But there are, of course, limitations to this satellite data, which we have to discuss. So as I mentioned, with that passive remote sensing, which is the typical technique that's used, that relies on the sunlight as its source of light to perform this remote sensing. And so in the absence of that sunlight, you typically don't get any data. This means typically no data at night, typically no data through dense cloud cover, and then very relevant for air quality, when there's very thick smoke in the atmosphere, which is blocking most of the light, you don't get enough signal to really make these measurements. Also, as I mentioned earlier, there's usually very little ability to distinguish where vertically in the atmosphere these interactions are taking place, which means that what the satellite's measuring, which is the sort of the column quantity, what's happening from the Earth's surface up to where the satellite's orbiting, may or it may not be well reflective of what's actually happening near the surface where people are living and breathing, which is the most relevant aspect for air quality. And then finally, there are limitations in terms of where and when the satellite can make its observations. And in a couple of slides, I'll go into more detail about that. But basically, based on the orbit that we decide to put these satellites in, it constrains when and where we can make different kinds of observations. So in the next couple slides, I'm going to go through some common basic terms related to satellite data. Some of these I've already been using, but just to clarify them so we know what we're talking about. Sometimes, and even I do this a lot, I use the term satellite and instrument interchangeably, but really what this means is the satellite is the spacecraft and the instrument is mounted to the satellite. There could be multiple instruments mounted on the same satellite, and the same type of instrument might also be mounted on multiple satellites. So they're not necessarily the same thing, but sometimes we do use them interchangeably. The terms swath or field of regard really refer to what on the Earth's surface, what the instrument can actually see. So in this diagram here, as the satellite's moving overhead in a certain direction, it's flying overhead, the instrument's looking down and it can see a stripe of the Earth's surface as it's passing overhead. So that would be its swath or its field of regard. The overpass time is really referring to when this instrument is passing over a specific location, and that's really governed by the orbital characteristics. So I'll talk a little bit about that now because I think it helps understand what these limitations are. So there are two common types of orbit that these satellites, which are measuring things relevant for air quality, are usually launched or put into. The first, probably the most common, is a polar orbit. So these are, as the name implies, passing over the north and south poles of the Earth, so orbiting in south to north and north to south directions. And these are typically, synchronized with the rotation of the Earth, so such that as the satellite's orbiting north to south, the Earth is rotating underneath it. And over the course of a day, the satellite's basically able to scan out over all or most of the Earth's surface in that way. Again, these are also usually synchronized with the position of the sun in the sky, so that when the satellite passes over a given point on the Earth's surface, it's usually synchronized such that that's happening at roughly the same local time of day according to the position of the sun in the sky on every day and on every overpass. So practically what this means is with a polar orbit, you have at least the chance to observe all locations of the Earth's surface, or most locations throughout the course of a day. But the way this is set up, it's constrained to happen only at a specific time of day when that satellite's passing overhead. And usually it's roughly the same time of day every day. A geostationary orbit, on the other hand, is farther out and it's synchronized with the rotation of the Earth such that the satellite is always looking down at the same part of the Earth. So this means it has more opportunities to observe that part of the Earth because it's always over that part of the Earth, but it's constrained to only observe that part of the Earth. It can't really move around to other parts of the Earth. We'd have to launch multiple satellites into similar orbits to observe different parts of the Earth with that strategy. So to summarize that, with a polar orbit, you get basically a once daily observation typically. Geostationary orbit, you get more frequent observations, but for a more limited subset of the Earth's surface. So I've talked there about related to those topics, there's equator crossing time, basically for a polar orbit, the time at which the thing's crossing the equator. Ascending, descending for a polar orbit, is it going north to south or south to north? And temporal resolution or return period. I talked about, how with a polar orbiting satellite, you typically get a 1-day return period. So the satellite will pass overhead once a day. And with a geostationary orbit, you get more of a higher temporal resolution. You get multiple observations per day, constrained really only by the presence of sunlight, for one, and then the ability of the instrument to collect data and for the satellite to then transmit that data back to the Earth. The next thing I want to talk about is spatial resolution. So when this instrument's looking down at the Earth's surface, it can resolve certain things depending on its capability at certain spatial scales, and we call that the spatial resolution. And typically when we talk about spatial resolution, or when we quote a resolution for an instrument, we're talking about the nadir resolution, meaning the resolution directly below where the instrument's looking. So it's looking directly down at the Earth's surface, versus if it's looking off to the side, it's looking at a bit of an angle, the surface is a little bit skewed, so the resolution at the edge of the field of regard, or the edge of the swath, tends to be a little bit lower because that same area is being now seen at an angle, so it's slightly larger. Just to kind of give an example of what we're talking about there, I plotted a couple of sort of the nominal or the nadir spatial resolutions of some instruments for measuring trace gases of the atmosphere on a map or on a globe, just to see what they look like. So you can see how some of the older instruments, GOM-2 in the red, Ski-Amaki in the yellow, and then OMI, which I mentioned earlier, launched in the earlier 2000s in the green, had spatial resolutions on the order of tens of kilometers. The more modern instrument TRPOMI in the blue in the middle there has a spatial resolution on the order of 3.5 by 7 kilometers for one of its image pixels. So you can see how basically over time this resolution has tended to be improving. This is different for different instruments, but that's been the general trend. Also, another key aspect is spectral resolution. So with this remote sensing, what we're really looking at is collecting information about the spectrum of light, so the intensity of light at specific wavelengths, which is shown by the red line in this spectrum spanning from the ultraviolet to the visible to the infrared parts of the spectrum. And the spectral resolution of an instrument really tells us about what parts of this spectrum can the instrument observe and how finely can it make distinctions between these different parts of the spectrums. And we typically categorize these types of instruments into two broad classes. The first is a multispectral instrument, where that's illustrated by the blue shaded areas in this diagram, where the instrument is observing spectral bands, so subsets of the spectrum, and it may observe many subsets of the spectrum, but those individual subsets are fairly wide. So it's a coarser or a lower spectral resolution. So it has less information there in terms of the spectrum, versus a hyperspectral instrument, which has a higher spectral resolution. So that's indicated by the orange regions at the top. So these hyperspectral instruments are measuring across a subset of the spectrum, but they're doing so at a much finer resolution. They can distinguish between those wavelengths much better. So practically what this means is that with the multispectral instruments, we have more limited information. And typically, for air quality purposes, these are only able to tell us things like aerosol optical depth. So how many aerosols are there in the atmosphere in general? Whereas for a hyperspectral instrument, we're able to get more information out of that data. So with those, we can really distinguish those the spectral fingerprints of different chemical species in the atmosphere. So these hyperspectral instruments tend to be able to give us more information about different chemicals species in the atmosphere, like nitrogen dioxide, sulfur dioxide, ozone, formaldehyde, things like that. And depending on what parts of the spectrum they cover, they can give information on different chemicals. So something that only covers the ultraviolet side or the visible part of the spectrum can tell us things about like nitrogen dioxide, sulfur dioxide, whereas things that go into more of the infrared part of the spectrum, like tropomi or skiamaki at the top there, can tell us more about more absorbing chemicals like carbon monoxide, carbon dioxide, methane, more of the greenhouse gases. But that's generally, the practical limitation there is that the spectral resolution really tells us about how much information we can get about the constituents from the data. And there is a trade-off there where a lot of the times, these multispectral instruments, they have a lower spectral resolution, but they typically have a higher spatial resolution, so they can get, smaller pixel sizes. And that's the trade-off that those instruments make. So I've talked about the spectral resolution. In terms of sort of managing the data, typically what these satellites do is they produce data products, which is some sort of output that's publicly released, telling us what the satellite data was able to capture. And those data products might be things like the column concentration of a gas in the atmosphere, as I mentioned, or the aerosol optical depth, the aerosol optical thickness related to the presence of aerosols in that field of regard. To sort of manage the data, we often split it up into discrete segments in some manner, and those are typically called data granules. That's the terminology that's often used. Just basically a data granule is kind of a file that contains some subset of the data that the satellite's collecting. And there's also typically processing levels associated with this data and then quality flags. So what that means is that at NASA and in many areas, we define the data in terms of 5 different processing levels. Level 0 is the raw information that's coming down from the satellite. And then at level 1, we take the information on the position of the satellite and where the instrument was pointing at a specific time to reference that raw data to specific locations on the Earth's surface. So that's georeference data. Now, typically, these are not so useful for air quality applications. Where we start getting useful information is at level 2. So at level 2, we apply the retrieval algorithm and retrieve or derive the geophysical quantities we're interested in. So basically the properties of the atmosphere that we care about. For example, in this case, the nitrogen dioxide column concentration. So again, these are now the georeference to the locations on the Earth, and it's a geophysical quantity, something we actually care about. As you can see in this image here, it's sort of it's still at the raw resolution of the satellite, so where each specific pixel falls on the Earth's surface, depending on where the satellite was. So that's a lot of information, and it's not necessarily easy to deal with because every pass of the satellite is going to be slightly different, so it'll have a slightly different, each pixel will have a slightly different position. So to work with the data more easily, we typically go to level 3 data products, and this is where we grid the data to a uniform grid, usually a uniform latitude, longitude grid over the Earth's surface, and we aggregate data in time. For example, collect all the data gathered over the course of a day for a polar orbiting instrument to plot out a map over the Earth's surface, like what's being shown here. There's still missing data there, and that's due to the limitations that I mentioned of not being able to retrieve information under certain circumstances. And that's also where quality flags come into play. So at the level 2, when we're generating those geophysical quantities, there's typically also a quality flag associated with each bit of information. So an estimate of how accurate we think that information is, or what may have gone wrong there. And in the level 2 data, that quality information is usually provided, but not necessarily applied to filter out maybe bad or missing data. At level 3, we typically do apply those quality controls. So we'll filter out data that don't meet a certain criteria for being included in the data set. So the level 3 data is generally easier to work with. because it's uniform, because it's gridded, and because these quality controls have already usually been applied to the data.